to lecture 13. This is not our last lecture, but we're almost done. Today I want to talk about multi-scale entanglement renormalization engines, or MERA. And I decided that it doesn't make sense that I spend half of my time drawing things on the blackboard. So I'll try, I see the value of working on the blackboard. I'll try to not go too fast, but still allow me to just focus on what I have to explain instead of just on what I have to draw. So summary of matrix product states, what we saw yesterday and the day before. We have the wave function of n sides, and that's given by, we can expand it in a local basis, and that gives us this tensor psi with n indices, I1 all the way to In. And we can diagrammatically represent it in this way. And we have this, 2 to the n or d to the n coefficients. And a matrix product state was this way of decomposing that tensor in terms of a collection of small tensors organized in a one-dimensional array. And its tensor had, if we assume that its tensor had a finite number or a number of parameters which was independent of n, of the system size, specifically we had Born indices, alpha and beta, which we are going to assume that take chi different values. And we had a physical index, which we are going to assume takes d values. So that should be here d to the n instead. Then it's clear that its tensor has d chi squared parameters, coefficients, and therefore we obtain that the total number of coefficients is only proportional to the number of tensors, which is n. So we have an efficient representation of the wave function. And we also discussed that there was a close connection between this and entanglement in the wave function. And the connection was this, that you can think of the MPS as a sequential singular value decomposition of this tensor, where you go to some particular cut and you say, OK, let me take all the indices to the left, put them together. This is one index. Let me take all the indices to the right, put them together. That's another index. Automatically, this becomes a matrix. Okay? And then you consider singular value decomposition of that matrix. Okay? And so there will be a number of non-zero singular values or Schmidt coefficients, and that's precisely the assumption here is that this number is chi. Okay? It's finite and it's independent. It does not depend on n. Very good. So MPS equal to a sequential to a sequence of singular value decompositions. And then we discuss, can we efficiently manipulate this? And I'm going to review this because it's going to be relevant to the discussion today. So efficient manipulation, well, the answer was yes, because we could sequentially contract, at least for the norm, we could sequentially contract this from left to right. There were some details that you explore yourself during a tutorial that told you how to do this optimally. And the result was that this could be done with a cost proportional to the system size again and to some power chi to the 3. And then if we wanted, instead of computing the norm, if we wanted to compute the expectation value of a local observable, we just had to put a matrix here in between, in the position of the observable. And there was this simple observation that turning this part of the diagram of the tensor network into something that looks like the calculation we did before was just a small calculation, small tensor manipulation, and therefore we still have the same leading cost. Okay, so we can efficiently compute expectation values. Look, so this showed us that we could efficiently manipulate that tensor network. We'll see the same properties with another tensor network today. And then we quickly saw also, or we also saw that there is some type of physics attached to a matrix product state, and that was entanglement entropy that was upper bounded by a constant, and that was easy to see because the moment we write the density matrix on some region in terms of the matrix product state, what we see is that the upper part and lower part of the density matrix are connected just by 2 indices. So that means that at most we have that the density matrix has chi squared non-zero eigenvalues, and that automatically gives us that the entropy is upper bounded by log of chi squared or 2 log of chi. Okay, we saw that saturation of the entropy. So it might be growing at short distances, but as you can see the region larger and larger, the entropy of the region, the entanglement entropy between this region and the rest is going to saturate. And we also saw correlations yesterday. And what we said about that was that if you try to compute a 2-point correlator, that again had some particular tensor network attached to it. And if you look closely to this tensor network, you would be able to rewrite it in terms of some vector, another vector, and some power of a transfer matrix in between. This was, if the 2-point correlator is a distance L, then this is L minus 1 power. And then if we assume that, or we can argue that the dominant contribution to this expression will be by every power here, we will pick up a dominant eigenvalue, and that eigenvalue will appear, therefore, to the L, or L minus 1 power. And so automatically, this leads to an exponential decay of correlations. Okay? We were saying a 2-point correlator is obtained as a result of multiplying order L times. And if every time you multiply, you get some factor L, or lambda, sorry, then you get automatically this exponential decay. Very good. So, and the conclusion yesterday was that structural properties of the MPS, which were the correlations decay exponentially, the entanglement entropy saturates to a constant, these two structural properties are in one-to-one correspondence with what we obtain, what we had seen the week before in ground states of 1D gap Hamiltonians. And so the idea was that perhaps this was a good ansatz for those states. Very good. So today we want to talk about another tensor network. And again, we start with having, our aim is the same as before, is to represent a wave function. We've been just reviewing matrix product state. Matrix product state would be an ansatz for ground states in one dimension. And the multiscale entanglement renormalization ansatz, or MERA, will also be a tensor network variational ansatz for ground states in one dimension. So what you can see here is that the open indices, okay, are also organized in a one-dimensional array. So you could imagine here that down here there are the sides of your lattice in the same way that we had it for the matrix product state. However, there are obvious differences. Maybe the most clear one is that this tensor network is not constrained to a one-dimensional array. It explores an additional dimension. Okay? Very good. So what I want to do today is to understand what the main properties of this tensor network are. And before we go into that, I want to clarify that there are different types of MERA in the sense that here you will analyze that there are different types of tensors, but there are basically two types of tensors. Tensors that we call these entanglers that map have two legs mapped into two legs. You have them up here, you have them down here as well, these squares map two legs into two legs. And then there is another type of tensor that we call isometry, which maps two legs into one, or in this case, three legs into one. Okay, the triangle here, it's mapping three legs into one. So these are details, okay? They don't change the properties, the fundamental properties of these ansatz. And so what I'll do today is I'll switch from one description to another whenever it's convenient, so that I'll use the description that makes the explanation that I'm trying to, that whatever explanation we are in, simplest, okay? So there is nothing fundamental, there is no fundamental change in using this one or that one, and I'll just use this to my convenience. Very good. So first question, efficient specification. Can we efficiently specify a state of n qubits using this tensor network? Okay, that's the first question we want to ask. And therefore, well, this is going to be a question about how many tensors we have here, given that tensors look finite and independent of the system size. And so remember that for the MPS, we had order n tensors, or n tensors, which led to order n parameters. And so the question for you is, how many tensors do we have in the MERA? The hint is that we have, in this direction, we have n open indices, and we have log n rows of tensors. Okay, there is 1, 2, 3, all the way to log n. Okay, so the first question is this going to be an efficient description? Okay, and today, since I'm not spending my time drawing stuff, I'll spend my time asking questions. So first question, how many tensors do you see? Order n, exponential in n. Are you counting them? Okay, so a good guess would be n log n. Okay, that's because it looks like n in this direction log n times. But if you count them carefully, then you realize that actually not all the layers are contributing as many. Okay, so let's count this more carefully. We have n open in the system there because we're trying to describe a system with n spins. So yeah, n log n tensors, and actually it's almost true, but if you count them carefully, you'll realize there are only order n, because if we break this into double columns, the first double rows, the first double row gives you exactly n tensors. Okay, the second double row gives you actually n over 2 tensors, and then n over 4, and so on, and you add this together, and it's upper bounded by 2 to n. So we actually only we explore an extra dimension, but we are still using order n tensors, and therefore the number of parameters that we need in order to specify this wave function remains order n. Okay, it would not have been a big deal if it was n log n, but just it's only order n. Very good. So yes, we have an efficient way of representing the wave function. It takes order n coefficients to specify a wave function on n spins. But we know that we have to answer other questions before we agree that this could be useful. So can we efficiently manipulate this wave function? And again, in the matrix product state, this was a question of, can we contract this? And the answer was, well, yes, we know how to multiply matrices sequentially without a cost that grows exponentially in the number of matrix multiplications, and so on. And we just discussed it, right? So I want to see how it looks, the same considerations, how they looked in the case of the meta. And so this is the wave function. Okay, there are all these tensors. And the first question I want to address is, can we efficiently compute this? Okay, and you should be suspicious that this may not be efficient, because we already mentioned that if you have a 2-dimensional tensor network, whenever we don't have a sequence of matrix, 1-dimensional array, but actually a 2-dimensional array, then that is typically not efficient. Okay, and indeed, we would not be able to efficiently, or the computation of this scalar product actually will require that I introduce an extra ingredient that I had skipped so far, which is that these tensors here are full of variational parameters, but by construction, by definition, okay, of the ansatz, they are constrained. They are constrained in that this tensor here is actually a unitary transformation. Okay, it's such that if I multiply by a joint conjugate, I'll get the identity. That's a constraint that I have from the beginning. It's not that I made it up now. I mean, I just didn't tell you for simplicity, but these constraints are going to be there. They form part of they are part of the definition of this tensor network. I also have this, that what we call isometries are actually such that W dagger. So when I multiply these 3 indices together, we get the identity also. Okay. So if this was a map from 3 spins into 1, what we're saying is that W dagger becomes the identity on the single spin. Very good. And then there is a top tensor up there, which also is constrained this way. It just means that that top tensor is representing a vector or state of 3 sides, and this state has been normalized. Okay. Very good.
We have the periodic boundary.
Yes. So in this particular slide, this leg is connected with that one. Yeah. And so this will be periodic boundary conditions. That's right. Thanks. Okay. So what's the cost of normalizing the wave function? I said I will be asking questions.
It's still order n.
Okay, my computation it was that you don't need to do anything. Because remember that we said that these conditions are there. Okay? So we just need to remember that the conditions are there. We just need to remember that they are there. And automatically, oh, I need.
You have to compute it explicitly takes you order n contraction.
Okay, very good. So let's see. Let's see that. So I welcome the guest, and now we'll see. So what I want to do is, indeed, I want to compute this. I want to contract this tensor network together, and I want to use these properties. Okay, and I want to show that actually we don't have to do anything. We don't have to compute it, which would be cost order n with a coefficient in front, 0. Yes. So the first thing I want to do is, this is U and this is U dagger, right? So we have this constraint, and I just want to use the constraint to see that U dagger can annihilate each other, and this will happen for any pair of disentanglers in the first row of the mirror. And so they are gone, okay? And I don't actually need to do it. The point is I know that this property is there, regardless of what variational parameters I choose, okay? So it's a property of the variational class. It's not the property of a particular optimized tensor network. Very good. And now I have this property, right? So after we remove the tensors in between, this W, this tensor W or isometry W, is directly connected to W dagger. So very good. Let's use that to remove all this layer of tensors. But now there we are. We have some disentangler here and another one there, conjugate. So it's going to go. Okay. And now we have isometries facing each other. So gone. And finally, we use the normalization of the top tensor to say that the answer is 1. Okay? So remember when we had a quantum circuit, we based our second example was a quantum circuit. In the quantum circuit, we never had to compute the norm because the norm was 1 from the beginning. So it's the same is happening. And actually, we'll see later that meta is nothing but a quantum circuit. So that property is expected. Okay? So what comes next? Now we want to compute. So we know that the normalization comes for free, but now we still want to explore how we compute expectation value of a local operator. Maybe an operator acting on two contiguous sides, okay? Two adjacent sides. So we know the rules. The upper part of this tensor network represents the ket. The blue square or rectangle here represents the insertion of the operator, and the lower part represents the bra, okay? So this is a number, there are no open legs, and that's precisely what we want to, it's this expectation value that we would like to compute. And so now, again, I'll use these constraints. The tensors are constrained in this way, okay? But, well, I can use that, and I can use that to simplify this tensor network a lot. Because, again, this U here will disappear with this one, and this will happen almost everywhere except in the neighborhood of this operator, right? Because, for instance, this unitary transformation cannot be simplified with this one. There is an obstruction in between. Once I'm done removing all these disentanglers, this isometry will be connected to its adjunct conjugate, and it will disappear again, and so on. So if I apply all these simplifications, what we see is that lots of tensors are gone, okay? But some of them are not gone. This U cannot be simplified with this one. As a result, this isometry cannot be simplified with this one because there is an obstruction and so on, okay? So what we see is that we started with a two-dimensional, what looks like a two-dimensional tensor network, and we ended up with something that, well, we will see, but there is some, we'll see that this is actually effectively one-dimensional in some sense, okay? And that's what's going to allow us to efficiently compute this. Very good. So our goal now is to analyze how to compute this in a way that the cost does not grow exponentially in the system size. So the first observation is that we can identify boxes. There is a pattern in this tensor network. And these boxes are the original blue one has 2 upper legs and 2 lower legs. Okay. Then there's another box that we can identify, which is the red one, which has 2 upper legs and 2 lower legs. Okay. And then there is the green one, which has 2 upper legs and 2 lower legs. So what we see is that there might be some computational cost attached to manipulating this, but there is some pattern that is being repeated. And so we'll use this pattern. In some sense, what we're doing is if we attach a notion of a scale, short distance scale and longer distance scale and so on, what we're going to do is a progression in scale. We're going to be multiplying things to move from one scale to the next one. Okay? And so the first one is the red box. What we see is that in order to go from the blue box to the red box, we have to multiply some tensors, okay? And there will be some cost attached to that. And I don't know how much it's going to be, but I don't see the system size either, right? I don't see this computation does not depend on the system size. So it's going to be some cost. Now, to go from the red box to the green box, again, we have some complicated calculation, but actually, if you look carefully, it's of the tensor network that we have here and the tensor network that we have there are the same. Okay? The tensors may be different, but the structure of the tensor network is the same. So it will have the same cost. Going from the blue box to the red box, or going from the red box to the green box, has the same computational cost. Okay? And what we're saying is then that we've been changing scale twice. Okay? From blue to red, we change scale. We consider a larger scale. That's the first change of scale. And from red to green, we change scale for a second time. What we're seeing is that changing scale comes with a fixed computational cost. Okay? And very good. And then finally, there is some final step there. So the observation is that we had to do something a number of times. How many times? Well, as many times as we had to change scale as many times as it's needed in order to go from the shortest scale in the system to the system size. And if you have a system of n sites, how many times do you have to change scale? If every time you change scale, you effectively halve the size of the system. So it's log 2n. Okay? We've done this before. There are only log n scales, or there are log n scales in your system. So whatever cost we had to go from here to here, we just have to do that log n times. So this is the cost. This is how the cost of the computation scales with the system size as a logarithm. Not exponentially, not even linearly, just as the logarithm. Okay? Very good. So now we have answered the question whether we can efficiently extract information from this tensor network. So what we do usually when we're done with seeing whether a tensor network can be efficiently manipulated, well, we look at what type of physics it represents. Okay? And so we look at the structural properties. We look at how correlations decay or how entanglement scales. And so that's what we want to do next. And again, we'll do this by comparison with the matrix product state. So we saw yesterday, and we reviewed briefly today, what happened in a matrix product state. Let's review it again, because we're going to do something very similar for the meta, but we'll reach different conclusions. So again, what we said is if we want to analyze a two-point correlator, we can write it as a problem of a transfer matrix that appears there to some power, and this power is proportional to the distance between the insertions. So once we have that, we have some eigenvalue, lambda, to a power which has to do with the distance between these two insertions. And that automatically gives you this exponential decay of correlations. Okay? So we want to see that a similar construction holds in the meta, but that the conclusion is going to be that we get power law decay of correlations instead. Okay, so let's have a look at that. We want to write a tensor network for a two-point correlator on the meta, and it looks pretty bad, okay? But we can imagine that this system is infinite, so n went to infinite. I'm also going to assume translation invariance, which means that this tensor and this tensor and this tensor, they are all the same. and this tensor and this tensor and this tensor, they are all the same, okay? So when you move horizontally, all the tensors are the same. I'm also going to assume one more thing. I'm going to assume that we are studying a scale invariant system. And when we study a scale invariant system, what we will use is, remember I was talking about going from here to here is a change of scale? Well, scale invariance will allow us, or will assume that it allows us to choose this tensor at this scale equal to the tensors at the next scale, okay? So translation invariance tells us in every given row of tensors, we're just going to choose the same tensors. Scale invariance tells us that different rows of tensors will also be, the tensors in different rows will also be the same, okay? So we're going to assume that, and we're going to see that this has an implication. We're going to be able to say something about the scale, how correlations scale in these answers. Okay.
Can I ask a question?
Yes, please.
In that tensor, like it seems to have two different kind of legs, like the two legs corresponding to the square box and one leg corresponding to the
Yes.
triangle box. Are those different legs are treated as equal?
Okay, very good. So the answer is not treating all the sides in the system on the same footing. As you point out, a side here or a side there, at the physical level, the lattice, we assume translation invariant in the Hamiltonian. So these two sides are identical, but the ansatz treats them separate in a different way. Okay? Yes. So what I'm going to argue is that what I will be able to argue in a simple way here is that when we put the operators that we want to study two-point correlator, when we insert the two operators in given places, okay, for those on those given positions, I will be able to argue that there is a power law of correlations. Now, this would be, and this property will hold before we optimize the tensors in the mirror. So this is a property of the variational class, okay? But that property is not clear. It's not clear that it's true also if instead of putting the tensor here, I would put it somewhere else. Sorry, instead of putting the operator here, I put it somewhere else, okay? But what I want to give you is some intuition of what's happening, and so I'm allowing myself for some particular cases, I put the insertions wherever it's convenient for me, and then I'll be able to argue how correlations decay on those positions. Very good. So we have this tensor network. Now we want to evaluate it. And the story is the same as before, right? The first thing we'll do is there is a disentangler here, U and U dagger, and so they will disappear. They'll disappear from almost everywhere, except in the neighborhood of the two insertions, because that's an abstraction, for instance. These two can disappear, but this one cannot disappear with this one, okay? So if you think about it, oh, by the way, what this means is that there is more tensor network, and the same on top, and to the left and to the right, but we will not need to worry about exactly what's in there. Very good. And where did I stop this drawing? I stopped when this line became nearest neighbor with this line, okay? Okay, so if I simplify this tensor network as much as I can, I get this, right? I just did what I said that I would do. I just used the properties of disentanglers and isometries to simplify them pairwise, and then I clean up many, many things. And what am I left with? Well, let me squeeze it to the left. What we see is some calculation that looks self-similar. There is something that is being done a number of times. To make it more explicit, I'm going to take the blue and red circles, the insertions, I'm going to pull them apart. And the tensor network, the same tensor network, can be redrawn in this way. Okay? I hope that's clear. I haven't done anything. I've just rewritten the tensor network. Okay? But now it's clear that there is something going on. There is some, remember I said that as an assumption of scale invariance, I could choose this tensor to be the same as this one and this one. What that means is that whatever this is, which you quickly identify as some transfer matrix, is the same as this one and the same as this one. okay, by a scale invariance. So moving in this direction or in this direction is moving in scale to longer length scales. And what we're saying is that we have some form of transfer matrix that is doing that for us. Okay? Okay, so let's do this calculation. Oh, we had this already. So, and I also want to point out that if these 2 points, these 2 insertions were at the distance L, after log L such changes of scale, they'll become first nearest neighbors. So how many times we have a transfer matrix here? Well, order log L, okay? So you see in the MPS, in order to go from one point to the other, there were L matrices, transfer matrices. Here, we have some similar structure, but instead of L copies of the transfer matrix, we only have log L copies. So there we are. So assume, as before, as in the MPS, that every time you have a transfer matrix, a copy of the transfer matrix, and there is a dominant contribution from some given eigenvalue. So what you will have is that eigenvalue lambda log L times. Okay, it will appear log L times. So lambda to log L. But also from the other side, so another lambda to log L, and then there will be some finite numbers that will appear, and I ignore them because they don't depend on L. And now there is this, okay, so we do this, right? So lambda to some, to 2 times log L. And now that's a fascinating mathematical inequality, or equality, sorry. It says x log y is equal to y log x. And if you don't believe it, just take the log on both sides, and you'll see that it's log x times log y equal to log y times log x. So yeah, that makes sense. So this allows us to exchange the lambda with the L. Okay? So what we say is if we have this eigenvalue to log L to the log L power, this is the same as having L to some power, which is log of lambda. Okay? And there we are. L to some power, and you could argue that this power is negative, that this is 1 to L to P, right? So L to the minus P. It's a power. It's a power law. There is a power law decay of correlations. Okay? Very good. Where this P is just what it has to be. So polynomial decay of correlations, again, as a result of the fact that in this tensor network, when you try to compute a 2-point correlator, you have a transfer matrix in a scale. This transfer matrix is acting a number of times, which is how many scales separate one point from the other, and that's log L. So instead of having some eigenvalue to the L power, it's some eigenvalue to the log L power, and that implies polynomial decay of correlations. Okay, so summary and interpretation of what we've seen for the correlations. It's just what I said, except that now we could go a bit geometrical and start thinking that what's happening is that we have a one-dimensional system. With the MPS, we use a tensor network that is trying to reproduce this geometry, a one-dimensional geometry. Okay? And so if you look at the distance within the tensor network, we could start talking about these 2 points being at some distance, where this distance is measured in how many tensors I have to go through before I connect one point to the other. Okay? So there is some notion of distance within the tensor network that in the MPS coincides with the notion of distance in the physical lattice that we're analyzing. So physical distance and tensor network distance are the same in the MPS. And that is what explains that we have this exponential decay. Because whenever we have we can think about these correlations as something, people get tired when they walk, right? So proportional to how much they walk, and then there is an exponential. So this getting more and more tired is expressed. If you lose something every step that you make, and what you lose is proportional to how much you have, then you find this exponential decay. Now, we can then interpret the result, the power law in the mirror, in very similar terms, except that we change the geometry that we need to analyze. Okay? So again, the physical geometry is clear. It's 1D. It's living down here. But now we are using an extra dimension. We are using a tensor network that uses an additional dimension. And then there is a sense in which we could, again, define distances within the tensor network. And what we would see is that there is this tensor network is attached, in some sense, to hyperbolic geometry. So what's happening is that there is a path to go. If you want to go from here to here, you could choose, for instance, to go up and down, up and down, up and down. Okay? And then you would find that inside the tensor network, this concrete path that I just described is, again, proportional to the distance, to the physical distance between the two sides. But there are shorter paths to be explored. Okay? And the shortest path that you can have always consists in going up in scale and going down again. Because if you do that, it turns out that 2 points at distance L in the physical geometry are connected by a path of size log L in this immersion geometry or this auxiliary geometry attached to the tensor network. Okay? And those who have been attending Pedro's classes, this sounds very much like holography. And indeed, this tensor network has been explored in the context of holography. I might be saying something about this tomorrow. Very good. So there we are. We have exponential decay in the matrix product state. We have power law decay in the mirror. And in both cases, we can interpret this as the result of having a geometry attached to the tensor network. So now I want to study entanglement entropy, and the reasoning will be connected to this one. So entanglement entropy, we've seen what happens with a matrix product state. We've seen that if we want to detach, in our wave function, if we want to detach a set of physical indices corresponding to some region A, what we have to do in the matrix product state is we can do that by cutting 2 bond indices. Okay? And this number of bond indices was independent of the size of region A, and that's what led, so the number of bonds that we had to cut was independent of the size L of region A, and that gave us this upper bound to the entropy that we could have, which was a constant. Okay? So the entropy of region A was upper bounded by 2 times log chi as a result of the fact that we can always break the wave function into 2 pieces by just cutting 2 bond indices. So what's happening in the mirror? Well, the situation is a bit more complicated. If we, for instance, again, if this is region A, and we try to find, what we want to do is we want to find an upper bound to the entanglement entropy of region A. And remember that an upper bound was given by how many indices we have to cut again, okay? How many indices are connecting that region with the rest of the system? How many indices? Well, every possible cut will give you an upper bound to the entropy. And for instance, if we just cut like this, if we split those physical indices from the rest by just cutting the tensor network down here, we'll again find that the number of, in this case, we'll find that the number of indices we're cutting is proportional to the region, L, okay? But this is only giving you an upper bound to the entropy. So to get the best upper bound, we have to find a way of detaching A from the rest of the physical lattice by cutting the smallest number possible of indices, okay? That's gonna give us the lowest upper bound. That's the best upper bound we can get. And then when you do that, again, you realize, oh, you can always go up in the geometry and then down again. And the number of indices that you will have to cut in that case is proportional to log L, okay? Because you are, again, going up a number of times, which is how many scales you have in the region, okay? Log L. Okay? So very good. We can cut this wave function, this tensor network, into 2 pieces by cutting log L bonds, and this implies that the entropy is upper bounded this time by log L. Okay? So it's an upper bound. It's not saying that it will have this entropy. It's saying that at most it will have this entropy. But that's the logarithmic correction that we wanted. So at least there is hope that these ansatz can reproduce the scaling of entanglement entropy that we observe in one-dimensional critical systems. Let's see this in more detail. So what we're saying is that the number of indices we have to cut to split region A from the rest of the lattice is log L. And let's just to illustrate in practice, you see, if region A had 2 sides, then indeed it's enough if we cut 2 indices. So in this case, we cut 2 indices. If it has 6 sides, it's enough to cut 4 indices. If it had 14 sides, it's enough to cut 6 indices. And so you see that this is growing fast, while this is just adding a constant every time. Okay? And that's exactly the logarithmic scaling, approximate logarithmic scaling that I was describing. Very good. So this answers the question of how entanglement scales in the meta logarithmically. So we saw power law, decay of correlations, and logarithmic scaling of entanglement entropy. And these are the properties that we know from ground states of one-dimensional systems, which are gapless or critical. Very good. So yeah, we're doing fine with time. Yeah.
Can you extract the constant in front of the law? Can you obtain the central charge too?
Not from this analysis, but this analysis, I hope I won't be able to extract the central charge because I have not optimized the ansatz yet. So this analysis is valid for any possible CFT, right? So there are details that will only become clear once I decide what's the system I want to analyze, what's my Hamiltonian, say, is it the criticalizing model, is it the XX model, right?
How do you implement that into the answer?
How do we optimize these tensors?
Yeah, how do you specify for a specific Hamiltonian?
Right. So this is not something I will discuss in detail here, but I'll tell you the basic parts of the story. So we know we can efficiently compute a local operator, expectation value of a local operator, right? And we know that that the Hamiltonian is a sum of local terms. So we know that for a fixed value of all these variational parameters, we have a meta for which we can compute the expectation value of 2-side Hamiltonian terms. So we can add all these contributions, and what that gives us is the expectation value of the energy, right? So having the ability to efficiently evaluate local observables implies we have the ability to evaluate the energy. And once you have that, you may find more or less efficient algorithms to exploit that, but basically you can change your variational parameters and see whether your energy is going up or down. Right? You change the variational parameters, you compute the energy, the expectation value of the Hamiltonian. And then if for that particular choice of variational parameters, the energy went up, you don't take it. If it went down, you keep that new choice of variational parameters, and you change a little bit again. Okay? So this is not how we do it in practice, but this tells you that the potential for energy minimization is there. Once you can efficiently evaluate local observables, you can use that to change your variational parameters in a way that the energy goes down. And then you keep doing that until you hit the bottom. And you hope that you don't get stuck in a local minima. Okay. Very good. So, okay, so what we have then is strong indication that this could be an ansatz, a proper ansatz for critical systems, and then we have to go and try hard. We consider specific Hamiltonians. We use these answers to approximate the ground state and see whether we succeed or not. Very good. I don't want to do this right now. I want to use the remaining of the time, the time that we still have, to relate this meta to try to understand what's happening. Why we've seen some properties, but now I would like to explain what these ansatz, what type of states really this ansatz is preparing. And it is useful in order to do that. I just switch from this 3-to-1 to 2-to-1 isometries, okay? the isometries now have 2 legs into 1 just because it makes this simpler. But there is nothing fundamental about it. I want to see this as a quantum circuit. Okay? I want to understand that this is actually closely related to the quantum circuit that we considered as a second example at the beginning of the week. But we want to also understand in which sense it is different, because that one didn't lead to an efficient calculation. Okay, so what I want, remember we have 2 types of tensors, the disentanglers, the ones that had 2 legs, that were a map from 2 legs to 2 legs. This was already a unitary transformation. And now I want to take the isometries and actually also regard them as unitary transformations in which one of the 2 legs has been fixed to state 0. Okay? So remember, this is an isometry. This times its conjugate was giving you the identity. And that makes it compatible with being extended to a full 2-body unitary. I'm saying this, if each index here took, say, chi values, then this has chi to the 3 parameters. This one here has chi to the 4 parameters. Okay, so there are more parameters here. So what we could do is extend this isometry into this construction where we would have more parameters, but then we would fix one index to 0. We can always do that. And then we can redraw the same tensor network in this way. Okay? And then finally, we do this. We just take all the zeros up. Okay? And there you see it. This is a quantum circuit. A very strange one if you want, but it's a quantum circuit. It's mapping, it's starting up here with a product state. And so you can understand a state that you end up having down here is the result of applying a sequence of gates to a product state. Specifically, let's think about this as a quantum circuit. And this time, the time of the quantum computation is fictional. It's not time in your quantum system down here. It's just some parameter that we use to characterize the quantum circuit. Okay, so, but then this is useful because what we're saying is that the ground state ansatz that we're considering is the result of untangling through some quantum circuit U an initially unentangled state, which is 0, 0, 0, 0. Okay? We start with the product state. We do something through a quantum circuit. And this allows us to actually analyze what's happening. There is a sense in which these gates, we start with a product state. The gates must be responsible for introducing entanglement into the final state. And what we see is that this is being done in a way that is very well organized, according to what we have started to call scales. Remember that as we go up here, we were saying we're moving to longer and longer scales, larger distance scales. And so if we look at this as a quantum circuit, what we would say is, well, we start with the product state, then we apply this gate here, which will only take 2 of the spins or systems, and the result of this unitary transformation will be a state which is no longer product state between these 2. There will be entanglement here, but the rest is still in a product state. Then we come and decide that one of the 2 spins that have been entangled already is going to be entangled with another one, which is in a product state. That's what this unitary is doing, and so on. You see a pattern here, right? We introduce entanglement step by step. But actually, these different times correspond to different scales, and what we're doing is we're introducing entanglement at different length scales, okay, in an organized way. And I want you to remember this toy model we had for critical systems where we had just pairs, singlets at different length scales. And that gave us the logarithmic correction in 1D. There was a toy model that we analyzed last week. And so this is similar. This is just introducing, it's saying the entanglement down here can be understood as the result of having added contributions at different length scales. Okay? Very good. So this would be an interpretation of the mirror as a quantum circuit. And now And I think it's useful because it gives you this picture that the final state that you have is the result of having introduced entanglement at different length scales, which is exactly what a critical system has. So no wonder that this will end up being a good answer for critical systems. Okay, there is, though, an alternative interpretation of what meta is. Okay, we just described it or interpreted the meta as a quantum circuit, and now I want to go to yet another interpretation. I want to understand the meta as being related to some renormalization group transformation. Okay, so this will be building on previous work on the renormalization group. It will build on top of the idea of spin blocking as introduced by Leo Kadanov, who in the past had taught here psi. And so what's this idea of coarse graining in real space, or what's spin blocking? The idea is that you have your original system. It's a lattice system. Each side, say, contains a spin. And in order to proceed, in order to understand the physics of the system, which is too large to be able to, for you to be able to deal with it computationally, you may decide to simplify it by blocking pairs of spins, so, or sides. These two sides are blocked into a single one. Okay? What this tensor network representation of the process means is that actually, and that makes a lot of sense, we're going to use this tensor. Okay? It has three indices, alpha, beta, and gamma. You can think of this as, let's see, first, if we just had two indices, you would agree by now that this could represent a bipartite state, right? This tensor is a matrix, and you could use it. There is an index beta and an index gamma, and so we could be representing some state of a bipartite system, and this, let me call it W. So W beta gamma would be a way for to expand a state of two sides in terms of a basis of one side and a basis of the other. Okay? What we are doing now is we're adding an extra index, alpha. Let me put an extra index alpha here. If we do that, instead of expressing one state in terms of a local basis for part A and B, we're expressing a list, a collection of states as labeled by alpha. Okay? So what we are saying is that this symbol here, what it's doing is representing a basis of states up here in terms of a tensor product of states down here. And in particular, if you wanted this basis to be orthonormal, okay, if you wanted that property to be true, if you wanted this new set of states to be an orthonormal set, well, that would amount to saying that there are some constraint of these coefficients when you plug it here. And actually, this constraint is exactly the one that we have, that we say W dagger equal to the identity. Okay? This constraint is nothing but this constraint. It's saying that we're going to use a tensor here to define a basis of a state on an effective spin in terms of the tensor product of basis for two of the spins, of the original spins, and that this set is going to be orthonormal. That amounts to saying that this tensor is an isometry. Okay, so we're going to take this coarse grain transformation and we're going to modify it. So instead of doing that, we're going to do this. Okay, we're going to use the same idea. We're going to use isometries. But we're going to add, before we do that, before we put two sides into one, we're going to insert, we're going to put what we call these entanglers before that, okay? And the question, of course, is why, or yeah, why do you need this? What is the effect of doing that? And to understand this, I want us to think about what happens with entanglement. So we're going to apply this transformation. This transformation is going to constrain the lattice, original lattice, into some other lattice. Now, I want us to think about what happens if the original lattice is in a state that has short-range entanglement. And for instance, in a state where these two sites are in an entangled state. Okay, these two sites are entangled. These two sites are entangled. Well, they're going to end up being the same site. So if the entanglement is defined as not having a product state, if the two sites become the same site, the entanglement is gone. Okay, very good. And the same happens down here. If there's entanglement between these two guys, but these two guys will become the same site, entanglement is gone. So that's good because in a renormalization group transformation, we are aiming at having a renormalization group transformation. In a renormalization group transformation, you want short distance details to disappear. You want to keep the essence of the phase. You don't want to keep microscopic details that are irrelevant. And you could think that short distance entanglement is part of these microscopic details that you want to get rid of. So we're glad to see that some of this short distance entanglement is gone from the picture as we coarse-grain the system. But now I want you to think about what happens if we had exactly the same type of entanglement, but between two spins that are going to be coarse-grained and become part of different effective spins. Okay? Suppose now it's, from the perspective of the original state, it's just the same. Instead of happening between this pair, it's this pair, but all the pairs should be equivalent. But the coarse-graining is breaking this translation invariance, right? Coarse-graining, again, as before there was a question about this, is not treating all the sides on the same footing. Ones belong to left of a pair, and ones to the right of a pair. Very good. So what happens if we coarse-grain this, actually, is that whatever entanglement we had here will become entanglement between two effective sites. And this is bad. This is bad because this was short distance detail, right? We were talking about short distance details. And this coarse-graining transformation, depending on whether these short distance details are here or there, will throw them away or will keep them. Okay? So that signals at the fact that just doing spin blocking fails to remove in a uniform way all short distance entanglement. Very good. And that's precisely the point of adding these disentanglers. These disentanglers are something that we add to give us at least a chance to remove short distance entanglement when the entanglement is between sites that are going to become parts of different effective spins. So you can, again, in this course, I don't discuss optimization of these tensors, but you can see that indeed, if there was short distance entanglement here, you could use this unitary to just change this state into a product state. Okay, and so it's gone. Right? So that's an important idea. We'll talk about it tomorrow in another context again. Removal of short range entanglement is something that thinking about tensor networks added to the discussion of the renormalization group. Very good. So then what's the meta? Well, you can think of the meta as just a composition of these coarse-graining transformations. You see? We have these entanglers removing entanglement. We have isometries taking two sides into one. We do it once. We go from the original lattice to an effective lattice. We do it again. We go to some other effective lattice, and so on. So actually, when we think about the meta as a tensor network for a ground state or for a state, it's actually more than that. It's a collection of states. Okay? It's many in one. Because if I don't look at if I look at the whole tensor network, I get some wave function. But if I don't think, if I just consider, if I ignore the first double row of tensors, I get a wave function for L prime. Okay, so psi prime. And if I ignore the first two double rows, then I have another wave function psi second, okay, for another lattice. So we have a collection of wave functions, not just one. Very good. Oh, look, who's there? Okay, so you can remove the layers. Nice. So the conclusion is that meta defines, apart from a collection of wave functions, you can now interpret this collection as an energy flow in the space of wave functions. You have not just a wave function, but a collection of them, and they correspond to descriptions of the same system and the coarse-graining. Okay? So they correspond to descriptions of the same system at different length scale. So then we can talk about can talk about the space of wave functions. Usually in RG, we consider the space of Hamiltonians, of local couplings, and we think about a flow in the space of local couplings. And there are fixed points and stable fixed points corresponding to gap phases. There are critical fixed or unstable fixed points corresponding to critical systems, so we could flow away and so on. So we can do the same, but in the space of wave functions. Okay? Very good. But so this is a tensor network that naturally leads to a flow in the space of wave functions, but there might be some resistance to new ideas. So the question is, okay, what happened to my, I'm familiar with having an RG in the space of Hamiltonians. I want that. I understand that. I've been reading about this for many years. So what happens here? Can I recover that? And actually, yes, you can recover that from the same tensor network. And the reason is very simple. The reason is that if we can use this coarse-grained transformation to coarse-grained local operators. Okay? So this is what a local operator looks like. It's the identity acting on all the spins, except for, say, 3 nearest neighbor spins, where we have a local operator acting non-trivially there, and then the identity on the rest of the spins. And now what we can do is we can apply this coarse-grained transformation. How do we transform? If the Hilbert space, if the vectors are transformed by a row of disentangled isometries, operators are transformed by that, and their conjugate. So we put, if we want to coarse-grain an operator, we do it this way. Okay? We put the coarse-grained transformation acting as a bra and as a ket. And then the first reaction might be this is a disaster because we started with a local operator acting only on 3 spins, non-trivially, the rest was identity, but now it's acting non-trivially. This is a mess acting, these are the effective spins for the effective lattice. But we see that our local operator, which was acting non-trivially everywhere except in a small region, now looks like it's acting non-trivially everywhere. But now we remember that we had these simplification rules, right? UU daga identity, WW daga identity. We apply them here, and we see that the coarse-grained operator, which was just acting on 3 spins initially, is actually, again, acting non-trivially only on 3 spins. Okay? So we've mapped local operators. This coarse-grained transformation mapped local operators into local operators. Very good. So, so that means that if you give me a local Hamiltonian, for which this construction gives you an approximation to the ground state, then I can use this construction to coarse-grain this Hamiltonian and get, again, a new local Hamiltonian. Okay? And then I can constrain it again by using the next layer of tensors and so on. Okay? So this picture is also valid still for Hamiltonians. This construction gives you how to coarse-grain the Hilbert space and therefore also how to coarse-grain operators acting on the Hilbert space, such as the Hamiltonian. Okay, very good. So yeah, I started 5 minutes late, so I'm going to take these 5 minutes. So I want to give you an example of how this works for critical systems. So the input, what you have to provide is your critical Hamiltonian. It could be the critical Ising model, X Hamiltonian, the ones that you've been dealing with at the beginning of the course. Okay? And then what we can do is we can use this. We already saw that we can efficiently compute the expectation value of the energy, and in particular, there must be many possible ways of optimizing the tensors using this possibility. So I'm not describing the details, but I'm saying take these ansatz, optimize the tensors in these ansatz. Okay? And now assume that you already obtained a good approximation to the ground state. Now this is one thing you can do. I just described how to coarse-grain local operators, how a local operator is coarse-grained into a local operator. So once you've optimized these tensors, you've basically optimized also your coarse-graining transformation, your RG transformation. And so you could take a local operator acting on 3 sides and map it into a local operator acting on 3 sides for the coarse-grained system. Very good. But now, if you don't do that for a particular choice of local operator, the blue guy here is the local operator. This is actually a linear map, right? Any local operator you put here, you get a coarse-grained operator. So what you have here is a super operator, okay, that takes as an input a local operator and it spits out a local operator. If you diagonalize this super operator, what do you get? You get local operators that under cosgraining are mapped into themselves. These are the eigenvectors of this super operator. So this is a direct way of getting the scaling operators of the theory. Scaling operators being the ones that are mapped into themselves under cosgraining. And if you do that, then from knowledge, so you optimize your tensors first, then you diagonalize this scaling super operator, and you spit out the scaling operators. And the scaling dimensions are given by the eigenvalues of this operator, this super operator that you just diagonalized. And from there, you can recover the conformal data of the underlying CFT. We talked briefly about this during the first week. There, instead of using this direct route, we were using some map, some correspondence between operators and states of the theory that was part of CFT. Here we directly go into what are the local operators that are mapped into themselves under rescaling. And by looking at their properties, we can extract the scaling dimensions, the conformal spin. We can extract other properties that we could not extract directly from looking at the energy spectrum during the first week. So the so-called operator product expansion coefficient and so on. Okay? Very good. And when you do this for, say, the criticalizing model, you indeed recover what you know by now. There were conformal towers, the identity, the spin, the energy density. We also saw the disorder operator, the two fermions. These are things that you've seen, but by diagonalizing the Hamiltonian. Here we are not diagonalizing the Hamiltonian. We go directly into the scaling operators of the theory. Okay, and then when you compare the numerical results to the exact solutions, this should be 1/8 or this should be 1 to 5, and big deal. You get an error, but it's not so big. This should be 1. You get again several digits of accuracy. This should be a 0 here. This should be a 0 here, and so on. You see that you get high precision results. So the idea is we assume that this was an ansatz. We assume that this was a good ansatz to represent the ground state of a critical state or of a critical system. That was an assumption. We argued why we thought it could be, but then when we tested numerically, we see that, oh yes, it was a good ansatz. Okay? You get properties about the two-point correlators at very long distances. There are these scaling dimensions decide these power law decays. Okay? These are the exponents in the power law decay. And these are highly non-local properties of your wave function. Okay? And yet you can get them with high precision. Okay, so we're done. So let me tell you how this fits in the big scheme of things. So last week we saw a scaling of entanglement entropy. We saw that in one dimension we had the area law, which meant saturation to a constant. And for critical systems, we had a logarithmic correction and different behaviors for 2 dimensions and 3 dimensions. That was last week. And this week, what we've seen is that we have tensor networks. And during the week, we've seen that matrix product states fit very well with gap systems in 1 dimension. Okay? The scaling of a matrix product state saturates to a constant. And meta fits very well with the scaling of 1-dimensional ground states for critical systems. Okay? And so what we can see tomorrow, one of the things we'll see tomorrow, is how to build tensor networks in higher dimensions that also fulfill the area law, or more generally also that reproduce this logarithmic correction to the area law.